Hello friends, this is a T-Kindle application named PorePressureCalculator. So this is developed in Python language using machine learning algorithms. So ROP is in feet per hour, weight on bit in kilopounds, bit size in inches. We have a widget to enter normal gradient and overburden gradient. I'm selecting 0.45 psi per foot as normal gradient and 0.65 psi per foot as overburden gradient. So there are two approaches to calculate the pore pressure in this application. One is using D exponent. The other one is using resistivity. Okay, let me select the data first. And here is my Excel file. Okay, the database is selected. And here you have the correlation matrix, which indicates how each varying parameters are related with each other. So basically, you have index, depth, ROP, weight on bit, RPM, mud weight, bit size, total gas, gamma ray, resistivity. As you can see, there is nothing against mud weight and bit size because they are not varying, because mud weight is kept constant, bit size is also kept constant, and hence the correlation matrix is not applicable to these two parameters. And the matrix says index to index is 1 correlation. Index to depth is also 1. Index to ROP. Of course, index to ROP or index to any other parameters doesn't make sense for us. So basically, ROP, weight on bit, RPM, and other parameters can be looked for correlation. ROP to depth, it's having a marginally positive correlation, and correlation number is 0.29. So that is 30%, approximately 30% correlation is there. And ROP to ROP is 100% correlation. ROP to weight on bit is only 14% correlation. ROP to RPM is 42% correlation. ROP to total gas is roughly 8 percentage or 9 percentage correlation. ROP to GR is 22%. ROP to resistivity is an inverse correlation, negative correlation. Okay. Uh, Although it may not make meaningful ideas, it helps to find how each parameter is correlated with each other. Okay, let's come out of it. Okay, we have the button for computing the exponent, and it computes the exponent and plots the exponent. Both the d exponent and the corrected d exponent are plotted. And finally, we have a pore pressure plotted versus depth based on d exponent using overburden gradient and a normal gradient. Okay, let's go for that. Compute d exponent. Okay, here you have the d exponent plotted, and the red line is the linear trend line. It is progressively increasing. As we progress on the depth front, the d exponent is also increasing, which means There isn't any um, any under compaction in this zone except maybe here, this portion or this portion, except that it's almost kind of a linear straight line. And I have plotted a curvilinear trend line also. This is for future developments, like uh, researching whether we can apply the exponent based pore pressure calculation for sandstone and limestone. That is later on. Okay. Now come out of the exponent plot. The exponent is plotted on the y-axis. Depth is on the x-axis. Okay. Now we have the d exponent corrected plot. So there also, after correction, overall it says that the exponent is increasing, but the d exponent number has value has decreased after correction. Correction is with normal gradient and current mud weight. There also we can see that this area and this area is slightly undercompacted, or rather we can say there is there is an increase in the pore pressure as we reach this area and this area. Okay, that is about the exponent corrected plot. Now comes pore pressure restricted plot. So here I have restricted the pore pressure value 8 as the base value, because any value below 8 is not reasonable, or 8.33 is not reasonable. So one can see that the pore pressure is gradually dropping from uh, this point to this point, and the maximum pore pressure based on the exponent is, say, 10.2 ppg, and yeah, 10.2 ppg, and progressively it is dropping. Now let me click the button for resistivity trend, compute resistivity trend, because this essentially plots the resistivity um, with a linear trend line and a curvilinear trend line, and thereafter it plots pore pressure based on resistivity, and after that it plots a restricted or restrained pore pressure to allow for variation, high spiky variation in the resistivity values. As you can see, in the beginning, in this area, we have a spiky resistivity, which can cause serious negative spikes in the pore pressure, because the equation obg minus ng multiplied by the ratio of resistivity observed to normal will give spiky negative variation for very high resistivity values. So to allow for the restraining of this spike, It is set, 8 is set as the base pore pressure. So before that, let me zoom here so that I can see how the pore pressure is, the resistivity is behaving. One can see that the resistivity is increasing gradually as it is normal because as we progress on the depth front, compaction happens and compaction expels water from the formation and that leaves the formation rather kind of an insulator. So the resistivity increases generally and compaction, normal compaction allows negligible increase in the pore pressure. So let me come out of that. And now I have the pore pressure calculated based on resistivity. But as I said earlier, you can see the negative spike here in the pore pressure. So this is the pore pressure plot, pore pressure plotted on the y-axis and depth on the x-axis. So if I zoom it here, you can see how it behaves. See, this is the pore pressure. The pore pressure actually is from ranging from 8 to, say again, I will zoom it. See, the maximum pore pressure here is 11.64. So this is less visualizingly appealing. So in order to make it more appealing, I have allowed for restraining the pore pressure spike by setting 8 as the base value. Okay, so this is the pore pressure restricted or restrained. So all those spikes get cut off at 8. So no more plotting after that. And this is generally the trend. The maximum pore pressure is 11.50. 11.50, yes. And generally one can see that the pore pressure is decreasing as the depth is progressing. So this is essentially the problem with the resistivity based pore pressure because resistivity increase can be often very high from the lowest of resistivity values and hence can result in spiky negative pore pressures. So the best approach would be to use sonic data, dt by ds or dn by do, which is normal sonic transit time to observed sonic transit time, observed transit time. So this is very useful for everybody, uh, and it is not very complicated. It is very simple. So what we have to do is to configure the database as per the algorithm and input the normal gradient and of course the overburden gradient, and then the plots are generated. So that's a very good positive approach. So thank you for watching. Thank you very much.